Good afternoon, everybody. Both here in the room and online. It's a great pleasure to introduce to you Jennifer Johnson from the Ohio State University. Jennifer is actually a PhD graduate from the UC Santa Cruz and was then a Carnegie Fellow and a Plaskett Fellow in Canada before she joined the Ohio State University in 2005, where she climbed the ladder to become a full professor. Jennifer is an observational astronomer, mostly into spectroscopy, stellar chemical abundances, the origin of the chemical elements, and interested in the Milky Way and the formation of the Milky Way. She's therefore also very much involved in the SDSS surveys. Already in survey 3, she was a very prominent figure, and currently she is in SDSS-V. She is the program head or chair, I don't know exactly how to call it, from the Milky Way mapper. So please, Jennifer, without further ado, floor is yours.
Right. Thank you so much. Oh. I love your optimism. Please feel free, if you have questions during my talk, to go ahead and ask them. There should be a nice question and answer session at the end as well. Yeah. At Ohio State, we show that we are listening by asking questions interminably. Okay, so today I'm here to talk about some recent work that we've been doing on understanding the origin of the elements and using the fact that there are stars all across our galaxy with different composition and that they're supernova remnants. With different composition that we can use to get an empirical view on nucleosynthesis. And this is just one of the many plots from the Apogee survey that's inspired me over my career. This is showing the metallicity as a function of position in the galaxy, superimposed on an artist's conception, alas. And you can see the very strong metallicity gradient going from more metal rich towards the galactic center to more metal poor towards the galactic outskirts. Now, of course, since I'm a full professor, that means I've done none of this work. So this work has been done mainly by Emily Griffith, who was a grad student with David Weinberg and myself at Ohio State and is now a postdoc at the University of Colorado. And Ari Bradal, who just completed her master's thesis with me and Laura Lopez at Ohio State. Now, one of the most exciting things, in my opinion, that's happened in astronomy over the past 100 years is the conclusive proof that stars make the elements in their lives and deaths. So going back to the 1950s and the really exciting work on the Big Bang, they did try and explain all of the elemental abundances coming out of nucleosynthesis during the Big Bang. And Burbage, Fowler, and Hoyle, most particularly Burbage, and Hoyle, did not. Oh, is there an issue? Right. So we know that the stars make the elements, and there have been a couple of really, hello examples of this. One of them is shown here on the left. So this bright spot right here is the supernova 1987A. It is an example of a star where we saw the supernova explosion. Then when we went back and looked at the maps of Sandulik, we found the blue supergiant that used to be there and has now exploded as a supernova. We saw the neutrinos coming from the neutronization of the material. We see enhancements in the various elements. We have not yet confirmed a neutron star in the supernova remnant, but there are arguments that it is that is showing itself up in certain emission from the supernova remnant. So this is one really nice example. Of course, we are all waiting for like Betelgeuse to do this so we can have a galactic supernova and we can all have, millions of neutrinos from that supernova pass through our bodies. On the right here, we have an example of a spectrum taken on a photographic plate back in the 1950s of our gem. Showing a technetium feature. Now, technetium, all the isotopes are radioactive. And in fact, if we made the entire Earth out of technetium at the beginning of the solar system, there would be no technetium atom left in the Earth. It would all have decayed. So it does have a pretty rapid half-life. And therefore, if we see it in the atmosphere of a star, We know that a star has had to make that very, very recently, otherwise it wouldn't be there. And so that's an example of a beautiful technetium line. It's not the only one, but this was evidence that Burbage, Fowler, and Hoyle pulled on heavily in their arguments that the stars make the elements. Okay, so now, having laid out the pretty picture that we agree that stars make the elements in their lives and deaths, we now start looking at finer details, and then we start seeing a lot of disagreements. So I crossed out the agreement between theory and observation. This is work from Brett Andrews et al., 2017. There's many other examples where galactic chemical evolution models have been compared with data. And so here we have for the solar neighborhood, we have observations, and it's the gray points. We have then a chemical evolution model here for the best fit using two different sets of yields. In cyan are the Woosley and Weaver yields, and the blue are the Lamongi and Chiaffi. And in dash blue, Brett just used the solar metallicity yields, not using the appropriate metallicity along, just to highlight what the metallicity effect is for these yields. And you can see that some things look pretty good. Oxygen looks pretty good, kind of like oxygen. Manganese looks pretty good, though don't talk to, the concern here is that these may not be correct elements because they are correct measurements because we haven't taken into account non-LTE effects, so on. And then there's real misses. Aluminum misses badly at the metal pore end. Potassium is right out. I mean, potassium would really like to be high, and we keep trying to make it much less high in the observations, and it keeps not wanting to be the case. Yeah, so there are definitely some disagreements here. And of course, we also can't observe all the elements. There are notable ones that are missing here, including very common elements like neon and argon and the other noble gases. That's just because they are not very friendly in stars of a range of ages. Okay, so what could be going on here? So the yields from core collapse supernova, the theoretical yields from core collapse supernova suffer from a lot of problems. I will say that looking at the literature over the past year, the supernova modelers are more optimistic than anybody else, than they've been in a while. So now many models that are 2D or 3D, so they can include effects like convection, now explode self-consistently. And I've given you some references up there. However, running a full suite of models where you vary the metallicity, you vary the masses, and we need lots and lots of masses because in order to do chemical evolution, we need to take a whole range of masses that have contributed to the galactic chemical evolution and follow along with them, is really problematic, and they haven't managed to do that. So for nucleosynthesis, I would say forced 1D explosions remain state of the art. And Hans Walter, do you have a question or an issue?
I apologize. So I did have a question on the previous plot, which you can answer later. My question was, you showed universally Fe/h is the x-axis. That is, of course, the historical choice. Do you think still it is the best choice for more than historical reasons? And does it make a difference in any of the contexts you talk about?
I will come to that point when I start plot. Yeah.
Okay, happy to wait.
Yeah, so the question, sorry, because otherwise I get the feedback from me. I'm having that issue. So Hans Walter was asking, the bottom axis here is Fe/h, and that has been usually the case because we can measure iron in almost every kind of star. So that was an observational constraint, maybe not the best theoretical way to think about it. And I will talk about why magnesium to hydrogen or oxygen to hydrogen may be a more useful way to go. But this does remind me to say that, yeah, so this is the ratio of iron to hydrogen on a scale where 0 is solar. This is a 10th solar, this is a 100th solar, and then this is the ratio of an element compared to iron. Again, solar scaled, so 0 is the solar value of these elements. So when we are looking at all of these nucleosynthetic yield sets, they are all 1D forced explosions. And the explosion mechanism matters. People have used a variety of methods. I will just say a couple of examples here. One way that people force an explosion is to put a piston, so they actually have mechanical energy pushing material out. This leads to enough energy going forward that there's very little or less fallback, so material has enough energy to escape, and rather than just not having quite enough and falling back onto the star. This is most important for material that's formed deep within the supernova, and that's the iron peak elements. So if you explode with a piston, you have less fallback and more iron peak production. Now you can also tweak the iron peak production when you're looking at your thermal energy injection, because if you inject your energy more slowly or more quickly, that also affects the iron peak production. If you have longer length of an injection, you get more iron peak production. And it's also well known that progenitor models matter. For example, how hard it is to explode can depend on the compactness of your core. The amount of mass loss is really important because that takes material away that then is not processed. And in particular, if your massive star does not explode, but collapses directly to a black hole, then the only elements that it's going to contribute to galactic enrichment are the things that are the winds that are blown out during the later phases of its evolution before it collapses. And rotation plays a major role in chemical evolution yields. The amount of rotation you can have, for example, can really up your nitrogen production by mixing between hydrogen and helium shells. And it turns out that maybe the reason why we're having such a hard time getting things to explode, or had such a hard time getting things to explode, is it's actually the case that a lot of stars don't explode, that they're really on a nice edge of having enough energy to do the fireworks display versus collapsing directly to a black hole. And this was proposed by Smart et al. In the 2000s as the red supergiant problem, which basically says that if you look at the stars for which, so we look out there, we identify a supernova, we look back and we see if its progenitor, look at its progenitor, determine the mass of the progenitor, and compare that mass function to the initial mass function of massive stars, that we were not seeing enough relatively high mass, and by that I mean like 17, 18, 19 red supergiants explode compared to what we would predict from the IMF. Now, Davies and Bezor, I'm mispronouncing her name, I apologize, have long argued against this, making points that the masses that were determined were maybe too low, and that it maybe is only a 2 sigma effect, not larger. And this is in part, it's hard to do. It's hard to do because you're looking at fuzzy HST. I hate to use the word fuzzy in HST, but it's true when you're looking at, things in Virgo that they're kind of fuzzy. And so your amount of light that you get from the progenitor is not super large. There's only about 24 of them that were being used in these kinds of studies. So, we're dealing with small numbers here. On this axis here, they have the initial mass in solar masses. Here they have the names of the various progenitors. And again, it's about 24. Here's the cumulative mass function. And they're in their work here, which are the blue points, they see that, again, it's about a 2 sigma effect. Kochanek in 2020 claimed more of a 10 sigma effect. This is his distribution of masses. He was claiming that if you did a Bayesian analysis, you ended up with these error bars wanting to go actually more to the left. I have not followed through on whether or not who is correct on this, but let's just say that there may actually be the case that not all massive stars explode as supernova. That has been noted in models as well. And yes, and this can have implications for nucleosynthesis, which we will come back to. I will also say that one thing I want to highlight here is that it is not surprising in this IMF distribution here that we haven't seen any 20, 25, 30, 35 progenitors identified. And that's a fact to stick in your brain. Again, the IMF is really working towards having things be more like 12 or 13 and less in the 30 solar mass regime. Now, if stars really don't go supernova, instead collapse directly to black holes, we should expect to see some. And this is work from the Assassin group at Ohio State, or sorry, the Survey for Nothing at Ohio State, led by Chris Kachanik. This is Adams et al. 2017. Here is the pre, here is the post. And, you know, there was a relatively bright progenitor. This is a progenitor. This is a steady thing. This is not a supernova. It's minding its own business here, and here it's not anymore. And the Survey of Nothing took regular observations at the Large Binocular Telescope, so they would have seen a supernova going here. The HST images are much better for looking for anything that's left behind, but again, we do not miss a supernova here. And you say to yourself, okay, well, I mean, that looks reasonably convincing. What could be going on here? Well, have you heard about what happened with Betelgeuse? This is from the American Association of Variable Star Observers plot. And oh yeah, horrible axes, but trust me, right, there's the great dimming of Betelgeuse, which was shown to be dust. And so the number one alternative hypothesis on what's going on here is that this star has belched out a whole bunch of gas, and that gas included enough elements to make a bunch of dust. And that's what is obscuring it here. It actually is not gone. It is just heavily obscured, which is one of the reasons why Adams et al. Was looking as much as possible in the infrared. So they're continuing infrared observations here to see if it's really gone. So those are some points leading up to our goal. We'll come back to those points in later discussion. Now I want to turn to what we can expect for a particular element, say oxygen to iron here, though we're going to also be free to put magnesium here for reasons I will explain. So oxygen to iron versus iron to hydrogen. And here again, we have in gray some local solar neighborhood data points. And in the red, solid lines, red, blue, and cyan, we have different predictions for one zone models. And what I want you to notice here is we start off at a reasonably high value of O to Fe. This is what core collapse supernova produce. They would like to produce a lot of oxygen, magnesium, silicon, and sulfur. Compared to type 1A supernovae, which really like to make iron and nickel and things like that. So the core collapse supernovae come from massive stars. They explode very soon after star formation has happened. So we're talking on the order of 10 to the 7th years, 10 to the 8th years, whereas the 1A supernova come from white dwarfs. There's a dispute over whether they're double degenerate, whether they're single degenerate, whether they need to be Chandrasekhar mass, but they definitely come from white dwarfs. And that's going to you have to wait for your lower mass star to evolve through a white dwarf phase, and then you have to get it to explode. So those start appearing later, and you can see here, there are various marks of the age here. So we start off with core collapse only supernova, and then we, as the iron from 1A starts to kick in, we start to drop down, and then we end up here, and we spend a lot of time in equilibrium where we have some gas falling in. That gas turns into stars, including massive stars. They contribute iron. Meanwhile, we've got a steady drumbeat they create some oxygen. Meanwhile, we have a steady drumbeat of iron from the type 1A and type 2s, all going along in there. So this is what you see, and depending on how rapid your star formation is, you can be kind of slow, so you don't get very enriched in iron from core collapse supernovae before the 1As also kick in, and you get this knee down. If you're very nice and efficient, you can actually get up to a fairly high amount of overall enrichment before the 1As start to kick in. So we see these different lines here, and so when we looked in the solar neighborhood, this is what we expected to see. No, put it out here. Okay. Got this two slightly switched up. So telling you various thoughts here. And part of the reason why I get annoyed. All right. So here's a periodic table I made of the origin of the solar system elements. And so it was, I was doing this because we had a presentation at an American Astronomical Society meeting, and I wanted a better graphic because the one in Wikipedia was wrong, so wrong. But I had to get it done by the next day. So like at 2 a.m. I had to make decisions, and I made some decisions. So for example, this abrupt change right here between zirconium and niobium is because it was 2 a.m. And so I made a switch here between saying that exploding massive stars can make up through zirconium, and then I'm like, the rest of the stuff comes from merging neutron stars. That is almost certainly not the case. That supernova should produce some of these heavy elements going up through here. I just didn't have any way to figure out how much they did. So again, 2 a.m. went for it here. Here's the technetium. Again, it's this color because all of the isotopes are radioactive, and there's and relatively short half-lives, and so there's none left on Earth that was made in stars. Yeah, but I have, various decisions to make here about which came from 1As, which came from core collapse supernovae, and I took my best shot, but there actually are fairly substantial error bars on all of these things. And as you'll see here, for iron, we're going to assume in the modeling that we do that not that more than half of it comes from white dwarfs, but actually that half of it comes from white dwarfs and so on. So here gives like part of my reason for really wanting better information. So I can revise this plot yet again. So this has already been revised because I screwed up boron. And I screwed up lithium. Lithium was even more complicated, but I would like to continue to revise this with better and better information. Okay, so how am I and Emily and Ari going to do this? We're going to rely a lot on chemical composition surveys. So particularly the Apogee survey, which is part of Sloan 3 and Sloan 4. And it's described in Majewski et al. 2017. It's H-band spectra. And in DR17, we had about 700,000 stars, mostly red giants. Some key elements, we have our carbon, nitrogen, oxygen, the alpha elements, again, those that are predominantly made in core collapse supernovae of magnesium, silicon, and sulfur, calcium as well, potassium because it's just annoying, and iron and nickel. And then Gala, which is described in Martel et al. 2017. This is the optical. It focuses in 4 optical windows of key elements. In DR3, they had about 600,000, many more turnoff stars, but also some red giant stars. And the key elements also include oxygen and magnesium, silicon, iron, and they also have some of the heavier elements, in particular yttrium and europium.
Jennifer Duffy, Hans Walter would like to ask a question, which I'll read out.
Okay.
Which processes did the Burbages think produced TC, whatever element that is? Oh, even if it does not live long.
Yeah, they nailed it. Because our gem was a low mass star, and they knew that it was an AGB star. They identified that it was through the slow addition of neutrons. So they identified it as the S process. Yeah, don't think they got the source of the neutrons completely, but they identified that it needed to happen over a long period of time. I don't know if that answers your question, Hans Walter. And so Apogee was done first at the Sloan Foundation Telescope in Apache Point, hence the APO part. It's the Apache Point Observatory Galactic Evolution Experiment. And there's a beautiful picture of it. We also now have a telescope at LCO down in Chile, so we're getting the whole sky. GALA, I forget what the acronym is, but it stands, because your Australian survey, you must be named after an animal. And here we have the GALA, the bird right here. It's a very pretty bird. Now, you may think that, GALA and Apogee have some pros and cons each, H-band, better seeing through the disk, optical has more heavy element lines, those kinds of things. But I say the main advantage that GALA had, and I'm kind of pissed about this, was the fact that they had observing help that we did not have. So there are the GALAs helping out at the multi-object spectrograph for taking of the data. Yes. They tweeted that out once, and they will live in infamy for that. Infamy. Okay. So chemical evolution, a little bit to the rescue to help us get an idea of the empirical yields of core collapse supernova and type 1a supernova. And how are we going to do this? We're going to rely on this very interesting fact / annoying fact that in the solar neighborhood, we don't at any individual Fe on H have a single alpha to Fe abundance. And here I'm going to use titanium as my alpha. I could have used magnesium, but this was the one that had the handy dandy axis labels. So that's what I'm using from Bensby et al. So this is a continuation of their work from the early 2000s that showed this very interesting fact. And we have two populations here. We have the high alpha, or if we want to be correct about the origin of the high alpha sequence, we call it the low 1a sequence, because there's a little contribution from the type 1a supernova. And here we have the low alpha or high 1a sequence. Okay, so we have here a lovely set of stars that have just core collapse yields. And here we have ones that have substantial contributions from type 1a, and sometimes we've got ones in the middle, and we can handle those too. So the initial assumption from Weinberg et al. Is that these stars up here, so if this for magnesium, it has a plateau at a similar point of about 0.3. So what we're going to conclude is that, so if magnesium over iron is 0.3 from pure core collapse enrichment, and it has to get down here down to 0 at solar metallicity, 0, 0, then half of the solar iron comes from core collapse supernovae. So we start off with twice as much magnesium to iron ratio that's twice as high as the solar ratio up here. And in order to get that to go down to solar, we need to dump in half again, that 100% more iron to get us down. Okay. So this is a very handy fact because it tells us here that what the empirical yields are for magnesium relative to iron. And we're going to use it as a crowbar to get across the rest of the galaxy. I just want to show this plot, and I apologize for the resolution. This is the famous plot from Hayden et al. 2015. Iron to hydrogen here, alpha to iron up here. And this is arranged in ascending height or above the plane or below the plane. So this is in the plane, a little bit off the plane, even more off the plane. And this is the inner galaxy from 3 to 5 kiloparsecs, and this is the outer galaxy from 13 to 15 kiloparsecs. So here we are hanging out about the sun right here. And what I want to point out is that the high alpha population here, and actually this line does an excellent job of marking it out. The high alpha population is very strong in the inner galaxy and above the plane. So it's nice and strong above the plane here, nice and strong in the inner galaxy. It is considerably less strong on the outer parts of the galaxy, down here, and high above the plane, or excuse me, outer parts of the galaxy in general. So high above the plane, low here, all not very fond of high alpha, but very strong here. And so this is just another way of saying that the high alpha population has a larger scale height above the plane, but a shorter scale height along the disk. So this is putting it in the correct geometry for being part of the thick disk. And if we look at the kinematics as well, the high alpha population is very tightly correlated with the thick disk population. Now, in another life, I am working on, along with many other people, how this bimodal distribution came about. What the heck is going on here? Is it these are stars that were brought from other parts of the galaxy and now inhabit this region? Is it that we were minding our own business, very happily going to low alpha, and then we got a big infall of fresh gas and headed back this way, and then are getting enriched again, etc. And so I'm hoping to use ages to help figure that out. But for now, I'm just going to move on. And from Weinberg et al., he did this division between the high alpha stars, low 1A, high 1A stars. In subsequent plots, those are going to be given as two different lines. So that's why we're showing you this plot right here. I'm not going to go through these in any amount of detail in the interests of time and brains. But what I do want to say is the two-process model, which Weinberg developed in this paper, relies on an amplitude of 1A over an amplitude of core collapse. And this is just using the magnesium to iron. So if this is 0.3, then there's 1A contribution. It's pure core collapse. We are allowed to have, so this is the production from core collapse for element X. It's allowed to have a metallicity dependence, which is this coefficient here, times the metallicity, which we define as mg on H. And we can determine the amount of ratio of 1A contribution for element X by this expression here. Okay, so we assume magnesium is only from core collapse supernovae, that magnesium and iron have metallicity independent yields. That's the only way we can get this to work. Or that's we can add additional features here to get that, to get it more complicated, but we're not. We're just going to do that there. Okay, so a qualitative exploration of how this works is we have magnesium to hydrogen here, and David Weinberg and me would argue that magnesium to hydrogen is actually a very helpful thing here, because if we cling to our idea that magnesium is only made in core collapse supernovae, then this steadily increases as essentially a measure of how many core collapse supernovae you've had. If you do it relative to iron, you're mixing up your core collapse and 1A yields. So you can have high iron either because you've had a lot of core collapse supernova, or you've had some core collapse and a lot of type 1A. And that's much harder to interpret. So we do it here versus magnesium to hydrogen, and here is calcium to magnesium. The low 1A is in the low 1A is in red, and the high 1A is in blue. What you'll notice, and these individual triangles here are the median sequences from apogee. So we just look back at that alpha to FE plot, took the stars in one, took the stars in the other, and found the median sequences. And here in the lines are fits to this from this two process models, and then you can see up here what the R1 like here, calcium comes 0.44, R1 is 0.5 from type 1A. In one fit, we use just the metallicity. There's only a metallicity dependence for the core collapse. And in the other model, we allowed metallicity dependence from both core collapse and 1A. And those are the differences between the lines. But what I want you to notice here is that it's pretty flat, which argues that they're not metallicity dependent yields. So no matter how much metallicity you have going on here, you don't get nice steeply rising things. You also see this very consistent separation. And the only way to explain that is to have part of calcium come from 1As. If calcium were only produced in core collapse, then the high 1A and the low 1A would not be separated at all in magnesium space, because your calcium to magnesium comes from core collapse here, your calcium to magnesium comes from core collapse there, and they should lie right on top of each other. And the fact that one of them has a lot more 1A should not matter at all. But instead, the fact that we have one sequence which has a much higher calcium ratio suggests that these here, which are the high 1A, the low alpha, have been boosted by contributions from 1A. So here are two examples of metallicity dependent yields. We have sodium rising steeply here. And again, this big separation suggests that there's a contribution. Now, maybe it's not from 1A, maybe it's something from that has the same delay time distribution as 1A, but there's a nice steeply rising point here. And then aluminum lies, doesn't matter if you have a lot of core collapse, or excuse me, a lot of 1A or very little 1A, your aluminum to magnesium ratio is exactly the same, which implies that both of them that aluminum comes from core collapse. And the 1As, number of 1As you've had doesn't matter at all. And again, a steeply rising thing here indicating metallicity dependent yields. Okay, and so Emily Griffith applied the same idea to the Galactic DR2, and she also updated a plot from Weinberg et al. 2019, and I really like this plot. This shows here the fraction from core collapse supernovae based at solar metallicity based on these this two-process model. And what I like it, so if you're up here at 1, you're all from core collapse. Okay, and obviously if you're 0, you're nothing from core collapse. And I just really want to focus right here on these. The black are Gala, the red are apogee. And we have comparison to Kempi yields from Rybicki et al. 2017. And again, some some heavy element yields, which I'm not going to discuss further here. So in some cases, you can see that Gala and apogee really disagree. Sodium is here one example. Sometimes, however, apogee and Gala are pretty much the same right here. And sorry, is that sodium? Yeah, sorry, excuse me, that's sodium. And they really disagree with the chemical evolution yields. So, you know, in the blame game, we're both responsible. And I will come back to that point. So there is disagreement between the empirical and the IMF integrated theoretical yields. Again, some of the most striking ones are sodium right here, aluminum right here, particularly for Gala. Excuse me, I'm gonna have to come over here. Yeah, aluminum. And again, like for cobalt, one agrees and one doesn't agree. And another interesting plot that she made was to compare with the Suckbold et al. 2016 yields, and with the Kempi yields. So if they're at 1 here, they agree with the element compared to magnesium. And if they're up, then they're overproduced relative to magnesium. So comparing the chemical yields to the theoretical yields, if it's up here, it's overproduced in the theoretical yields compared to magnesium. And if it's down here, it's underproduced relative to chemical evolution yields. So we see some, pretty strong disagreement. These are from the Woosley and Weaver. So Suckbold was working with Stan Woosley, and that's pretty consistently underproducing magnesium is, I think, the safest way to say it. So what could be going on here? I'm just going to say a single thing here. So abundances disagree. That could be partly our fault. Oxygen here is horrific. So magnesium versus hydrogen to oxygen to magnesium. The colored points here are Gala, and the black points in the background are apogee. Yeah. So we have possible issues. We need to work on this, and I'm thinking of various ways to working on this. And another thing that could be happening is that assumptions could be incorrect about the metallicity dependence of the magnesium yields, etc. So one of the things that R.A. Bradal did was to compare a whole bunch of different yield sets with this to see if some of them did better at producing the right amount of magnesium. So Woosley and Weaver, Chieffi and Lumongo, Nomoto et al., Suckbold et al., 2016, Lumongi and Chieffi, etc. And, there's a fair number of points that really like to high up here. If anybody does a reasonable job, it's Nomoto et al. 2013, but I wouldn't say that anybody was hitting a home run. So clearly going to a different yield set isn't going to solve this problem. So nope, not really. All right, so another idea is that actually in doing IMF integration over all the mass models that we have is a problem. It's incorrect. And so this is work from Emily Griffith and Tuggelder-Suckbold in 2020, masses on this axis. And these are the individual points lines here mark the masses that Tuggelder ran to see if they would explode. The grays marks the ones that don't explode. And so you can see we go through this black hole cavern right here before starting to come out again the other side. And we have this little island of explodability. And then like this one here is my favorite. It's like nope, yes, nope, yeah. And there are 2 different ways that he tries to explode it based on different calibrations to supernova 1987A. That's W18 and N20. And then in this work, one of the key things that Emily and Tuggelder did was to come up with a way for these of having a subset of these models so they could sample this region all explode. So is the problem for T's yields, for Tuggelder's yields, that those things really should have exploded. And if we could get them to explode, we would have enough magnesium, for example, in order to solve the problem. Hint, no. But they had to do some scaling here because if they were just doing it according to the initial calibrations, the things really didn't explode. So there's an interesting discussion in the paper about how they got enough energy in there in what they hoped was a physically realistic way, or at least not physically completely unmoored. And so what Emily Griffith then here did was to plot the element versus magnesium, and here are all your elements down here, comparing ones where all exploded from the new Tuggelder yields. Everything up to 40 solar masses explode, and then the 2 explosion landscapes that he had originally done. And you can see nitrogen very responsive. Oh, and these are all, excuse me, all scaled to magnesium. Nitrogen very responsive. And in general, there's a nice chunk of these dark things coming down, which helps with the quote unquote underproduction of magnesium, right? We're getting things closer, bringing them down. But I wouldn't say that this is a conclusion. This does not solve the problem, but it is interesting, again, as we move forward, to consider how nitrogen, for example, yields could be affected by these assumptions about black hole landscape. So chemical evolution is awesome in many respects. We can kind of use almost all the stars that are out there. But it is integrated, right? It's looking at the integrated IMF. And, for the sun, 1,000 core collapse supernova or so have contributed to it. So it's like a little bit tougher. So working with Ari Burdell and again, Tuggelder Suckbold and Laura Lopez and Tyler Holland Ashford, we went after abundances in individual supernova remnants to see if they did a better job of agreeing with theoretical yields. So Tyler is an expert, a guru in understanding how to take things like this and turn them into masses of oxygen and masses of iron and masses of magnesium. We looked at 11 core collapse supernova remnants. And so we really needed them to be core collapse. They couldn't be 1A. How did we identify that? If they had neutron stars in their center, that was great. If they had light echoes like Cas-A showing that they are 1A or core collapse, that's great. But often we had to rely on the fact that they were oxygen rich, with the idea that core collapse produce a lot of oxygen and type 1A really just go for the iron peak. In Cas-A supernova remnant, this is from Chandra, false color image, but it shows one of the main issues that we have, which is these different colors represent different chemical elements, and you can see it's very inhomogeneous. As the interior parts you might expect to be more iron rich, the outskirts more oxygen rich. So there's a detailed discussion in the paper of how we tried to get the best kind of total information for these supernova remnants. Okay, so this is again from Ari's work. We have here a couple of different ratios here: silicon to magnesium, sulfur to magnesium, oxygen to magnesium. And here we have listed the different supernova remnants. And if it is a slightly bolder font, it's an oxygen-rich supernova remnant, just to separate those out. And we don't know what the initial masses of the supernova remnant, the star that went off in the supernova remnant. So we just indicate the observations by these lines with error bars on them. And the black points represent the individual models. For Woosley and Weaver, Chiaffi and Lamongi, Nomoto et al., Suckbold et al., and Lamongi and Chiaffi. And if they're open here, then these are the forced explosions. The one they did not explode in the original one. A couple of points to make. First of all, Cas-A, man, has not very much magnesium. It's this line up here. Really nobody does a great job of matching Cas-A, but Woosley and Weaver and Suckbold et al. Do the best job of reaching close to there. Nomoto et al., these guys nowhere close. And again, I think Suckbold et al. Do the best job of spanning the range of sulfur to magnesium or silicon to magnesium that we see. Chiaffi and Lamongi are way, way, way too tight. They really don't do enough of the range there. Overall, however, we do see that there are a number of supernova remnants that lie below the one line here, which makes them more magnesium rich than Emily's integrated yields we're showing here, which is this dashed line. So they're down here, they help our problem. If they're up here, they also are underproducing magnesium. So I think one thing I would take away from this is that, you know, for individual abundance ratios and supernova remnants, we can find, particularly among the Woosley and Weevil and Suckbold et al., a model that works okay, right? At least for these isolated elements or isolated ratios. But what happens if we want to compare all the elements that were measured? And this is a particularly well-measured supernova remnant, G292. So here we have all the elements that got measured. There's some lovely things here like argon and abundance ratios relative to silicon, because that's one of the best measured elements in here. And here we have Woosley and Weaver, and we have the different yield sets down here, and the observations are obviously the same for each one. I want to highlight here argon. I'm going to come back to that. Everything sucks when it comes to argon. Nobody does a good job of measuring it. Woosley and Weaver does maybe the best job, and actually somebody tried. Oh, and sorry, these are different masses up here, all quite heavy. And in work, people claimed that this was a 30 solar mass progenitor because that was the best fit Woosley and Weaver one. But you see, if you go to different yield sets here, this really, I mean, you should not, I mean, Kathy and Lamongi would say there's no mass that fits here. So it's really problematic, I think, to infer the progenitor mass from abundance ratio yields. And so Ari also did, she tried to find the best fit model for each of these abundances. Cas79 also has a bad argon problem here. If we measure argon, which we do here and here, it just doesn't fit well. We have, again, so there are a variety of things, and in general, we do a pretty good job. We can always find an element that, a supernova model that fits. However, if you look at this, right, you quite frequently get things like 30 solar masses, 26 solar masses, 21 solar masses. My favorite, 120 solar masses. This doesn't look like the IMF that we would expect at all. Now, maybe it's in part because half of our supernova remnants are oxygen rich, and maybe we would only identify them as oxygen rich if they were from things like 20 or 25 solar masses, but half of them are not, and it still seems it's really biased high. So this is one concern that we have. Another concern that we have is sometimes we get really, really good fits because we have only a few measured elements. And actually, in individual yield sets, you know, there are a whole bunch of models that have very similar ones. So without too much difficulty, you can really do an excellent match. In some cases, you can never get a good match. But we can also see how unique these solutions are. So this is for the Suckbold et al. Yields. Here's the initial mass. Here's the supernova remnant. And you should look at individual supernova things. There's just a chi-squared over here, but Cas-A always looks pretty bad because of that very high amount of silicon to magnesium, oxygen to magnesium. So does Cas-79 because of that argon point, where some of them look very nice because we only have a few measurements. However, you can see here that, you know, for this one, there are a whole bunch of models that will fit really well, and saying that a 35 solar mass one is the one that works the best, well, kind of ignores this little gap here, etc. And so there's a whole bunch of, I would say, degeneracy in reading off the models. Go on ahead. So where does that leave us? So I would say that I went into the supernova remnant work thinking that this was going to be, completely depressing, maybe, that they were all going to underproduce magnesium and we were kind of be stuck. I think that's not true. I think that there are a number of the supernova remnants which suggest that there are some stars out there that produce enough magnesium, more in congruence with the empirical yields. What I also think is, however, that the masses that we are getting from the best fit yields show there's a long way to go because they are just not representative of what we'd expect from an initial mass function. And it's even worse if you try to take into account population, the binary black hole landscape. Okay, so what can we do in this? I think we can start to use 3D simulations to inform 1D work. And so Falk Herwig, among others, is working on this when there are very specific things that we want to make sure we get right. Like convective mixing. There are some shell intricacies in Tuggelder's work that I think we'd like to see if that's actually correct and holds up under 3D simulations. And then we can take the results of that very intensive 3D-ness and take a relationship back and input it into the models. I think another really exciting thing is that most massive stars are in binaries, and binarity can have a big effect on the yields. So you can have additional envelope stripping that can affect the yields. Rachel Patton at Ohio State is now looking to see what happens if you merge post-main sequence, what happens to your oxygen, your carbon-oxygen core, which is key for later nucleosynthesis. We need to improve our chemical composition measurements. And so we've had some exciting discussions among Milky Way Mapper and Foremost on this, and additional understanding of the origin of the elements. And to do that, I just wanted to say one thing. So Milky Way Mapper is awesome. I'm happy to talk endlessly about this, but instead I will say that one of the things I'm looking forward to is the local volume mapper, which gets ionized hydrogen H2 regions in the Milky Way and can finally give us argon in a variety of metallicity regimes where it's been very painful to do so far. So I apparently did not get a reaction from my chemistry joke, but I want to end on a plea that we get lots of argon measurements from local volume mapper. Thank you, and apologize for all the technical difficulties.
Thank you very much, Jennifer. Very, very important story, this, but it seems that there's a lot of interesting new factors coming in, which I at least didn't know about before this talk. I'm sure other people also want to ask questions. So first question.
Hi, Jennifer. Long time since we
Yeah.
see each other. So, very interesting work. You got a lot of information about this core collapse supernova insights and issues. So for modeling the Milky Way evolution, yeah, our hope was that from the yields and evolution, we can learn a lot about the star formation history. Now, we didn't talk much about 1A explosions.
Right.
I mean, the yield, relative yield of iron depends not only on the IMF, but also on the star formation history because of the long delay. Yeah.
Yep.
So that's our starting point. Yeah. But what about AGB star enrichment? I mean, many elements suffer or got AGB.
Yep. So in subsequent papers, Emily thought a lot about the S process, the AGB star enrichment, and I totally did not go into that at all. In the most recent, one of the most recent papers, she added an AGB component so now it was a 3-process model. So we could have core collapse, 1A and AGB, because we think the AGB should be on a slightly different time scale than the 1As. I would refer you to that paper. If there's a specific, so I think we're worrying about that as well. And for some elements, it definitely improves things to have that, but for many of them, it doesn't. And one of our problems, of course, is that we don't have a lot of S process elements, particularly in apogee. So so we haven't been focusing so much on those. I don't know if that answered your question at all. Okay.
Okay, thank you very much.
Thank you for these interesting results. So I'm particularly interested in these supernova remnants that you showed. I found it really, really interesting that there are some of these supernova remnants that really don't seem to match any of that don't seem to match with the models. And I was wondering if you could comment on the type of the of star that produced these supernova remnants, and if potentially some of these could be strip stars, for example, that could give different yields just because they come from stars with different core structures.
That's a really good question, and my answer is going to be very pathetic because, I mean, there's no among these supernova remnants, there's no obvious case of like having 2 neutron stars hanging out in there or anything like that would have told us it was a binary. And I think for CAS A, somebody can correct me if I'm wrong, that the light echo, which is the most awesome thing ever, shows that it's a standard type 2. It is not a 1B or 1C, which I would love to have for all of these for exactly the reason you're talking about. Yeah, that is my frustrating answer there. I do hope again that with the noon yields from starting from stripped envelope progenitors that we will actually start to be like, oh, maybe we should look at that. Maybe we should look at that. Yeah, good question. There's no obvious answer, obvious case where the answer is yes.
Okay, coming back on that.
Maybe I just can point you to some recent work from Farmer et al., where we actually looked into the yields for stripped supernovae.
Yeah, no, that's who I was thinking of.
Yeah, exactly. Yeah, and we saw that they are actually quite different.
Yeah.
Compared to the classic core lab supernovae, so that could be one of
the work faster.
Yeah, thank you.
Excellent. Norbert Christlieb has a question.
So
the Milky Way.
Christlieb has a question. She asked, can you please tell us more about the Milky Way mapper, such as FOV, number of fibers, spectral resolution,
Thank you.
wavelength range, etc.
Yep. Thank you, Norbert. So the Milky Way mapper is part of Sloan 5. We have 500 fibers in the north, 500 fibers in the south on robots. Yes, we have fallen prey to the robot overlords along with Weave and Desi and Foremost. So 500 of those, if wanted, could go to the BOSS RF2000 spectrograph, optical, so very similar to the previous SDSS spectrograph. And 300 of the fibers, if desired, can go to apogee. So there could be any mix of apogee and BOSS, up to 300 apogee, up to 500 BOSS. So depending on the targets and the faintness, we are spending a lot of time with apogee in the plane, going after about 4 to 5 million red giants to really do the chemical cartography of the disk. With BOSS, we are going after fainter halo stars. So the Halo group has been really awesome about it. Hans Walter and his group should know a lot about this because we're using their metalpore star catalog from Gaia XP spectra. I'm using other ways for finding metalpore stars, looking out in the distance there. And there have already been some very interesting one-offs. One of the things I didn't talk about here, which is also driving me crazy, is how badly we do with so many of the very metalpore stars. And we find unique abundance patterns all the time, and we have a real trouble getting supernova models to match. If Norbert has a disagreement on that, I'm happy to hear an update on that. So a whole variety of things. I think compared to other surveys, we have a couple of advantages. One is we're both north and south. The next is we are infrared with apogee, so we can go to the disk with impunity. And finally, we have at least some of a time domain aspect to it for getting binaries for O and B stars, getting binary fractions for looking for the brown dwarf desert. And so we have few epochs for lots and lots of stars to help with understanding stellar populations.
Okay, thank you. You mentioned earlier on this intriguing idea. I think you put up a survey about Adams, who is looking for stars which disappear without an accompanying supernova. And I wondered if there was a number which is coming out of this, which is known as yet, as to what fraction of those disappearing stars might be really disappearing, or alternatively, whether these were becoming infrared sources, which you mentioned as an alternative. And is there some infrared survey, e.g. with JWST, to follow this up?
Yeah, good question. I would say that we have, again, demand that Chris Kachanik be here next to me to give a more complete answer. I want to say there's 2-ish candidates, which is about what you'd expect given the number of stars that they've looked at for how long that they've looked at it I think Ben Davies thinks that maybe they shouldn't have found any, but from Chris Kachanik's calculation, this is about what they would expect.
Yeah, okay. I mean, has this any relation to the lack of supernovae being seen in the Milky Way?
Oh,
Probably not, because
Probably not,
you've got a very small percentage, I
Yeah,
guess.
again, right, because all the models don't think it's the 12 solar mass stars that have trouble exploding. Like, and whenever they do theoretical yield, and and the red supergiant problem is again at is it the 17 masses? Can 17 solar mass stars explode or not? So it would be surprising to me if that was the real impact, because I think again you're expecting at the high end of the IMF, and there's just not supposed to be that many. So, and many of those stars even. Yeah. Yeah.
It's fascinating.
Yeah.
Yes.
Yeah. It's again, it's frustrating. I mean, from the observational standpoint, it's very frustrating that it's supposed to be such a rare event, but such an important one. But, with LBT and the very kind OSU TAC who think that, well, they're also doing tons of side projects with this data. They can keep going on this. And I do think they've asked for JWST time. I'm not sure they've gotten it to look back at this source.
Okay, so it just remains me now to thank again Jennifer for telling us all about this very important topic, and thank you very much, Jennifer.
Thank you.